2.2c, part 3. We're still talking about end behavior. And last video we talked about using end behavior to solve some limits at infinity. And if you remember, we ran into a problem. In fact, I can show you right here where the problem was. We were looking at this limit, and we realized that the end behavior models we know how to find really only work for polynomial and rational functions. And so we need some new strategy to talk about end behavior of other major function families. And it's not a very sophisticated strategy. We're actually just going to memorize the end behavior so that when we combine them, we can follow a few simple rules. Let's start by talking about functions that you know, and we're going to categorize the functions that you know according to their left end and right end behavior. And you're going to do this just by thinking of what the graph looks like. So for example, let's start with the function f of x equals x. It's a totally simple function. Think about this function for a moment. What happens to it on the right end? What happens to it on the left end? Great, so if you think about the shape of this graph, it's a straight line, and the right end goes up to infinity forever, and the left end goes down to infinity forever. So I'm going to take this function, I'm going to categorize it as a right end positive infinity and a left end negative infinity function. And actually, while we're at it, the truth is any polynomial with an odd power. This is an odd power because it's really x to the first power. But if we talked about f of x equals x cubed, we would have the same end behavior, a different shape, but it would go up on the right and down on the bottom. So I'm going to go ahead and generalize. X and all odd polynomials are going to have positive right end behavior and negative left end behavior. Of course, we could change that by transforming the function. So these behaviors that we're writing down aren't fixed. It's literally just for the function parent. If I put a negative in front, if I divided it by something, the behavior could change. But this is kind of like a starting point. Let's try another one. Let's talk about x squared, another simple function. Where would you categorize this one? Right, so x squared, normal parabola, you know what it looks like, and you know that both ends go up to infinity. And of course, you may guess that I'm going to extrapolate that actually all even. If you think about a quadratic, sometimes I draw a quadratic like this, although actually x to the fourth looks more like a parabola. But enough said, even polynomials have positive end behavior on both ends. Great. So next function. How about the square root function? What do you think? This is where it actually gets fun. The square root function, which looks like this normally, unless it's flipped, actually does go to infinity. Now it goes to infinity much more slowly than other functions that we might like. It's kind of curved over, but this side does go up forever, and it's really important to remember that when you're drawing it. It's not a horizontal asymptote as much as we might accidentally make it look that way. The left-hand side, however, stops existing. It doesn't go to the left, really. So on the left-hand side, the square root function doesn't exist. And on the right-hand side, the square root function goes to positive infinity. How about the cube root function? So the only difference between the cube root and the square root is that the cube root does have two ends. And this comes from the fact that you are allowed to take a cube root of a negative number. It just equals a negative number. Looks something like this. Imagine a cubic kind of reflected over the y equals x line, inverse functions. And just like before, we may accidentally draw these as if they are horizontal asymptotes, but actually both ends continue traveling. This one travels up and this one travels down forever. And that's something that you just have to know because the graph might not always really look that way. But if it's a cubic function, sorry, a cube root function, the right end behavior is going to go to infinity. And the left end behavior is going to go to negative infinity. Next one. 1 over x. Great function. All right, so you're very familiar with this one. This is the two-part function that has both vertical and horizontal asymptotes. Right now we're really only interested in the horizontal asymptotes though, because the right end of this function gets closer and closer to 0. And this is actually an asymptote. It's a true asymptote, and both sides have true asymptotes. So this is our first constant end behavior. And it's constant both on the left and on the right. In fact, they're actually both approaching the same number, although that doesn't necessarily have to be true for all rational functions. How about natural logarithm? Great. So we're starting to get used to this. Natural logarithm is the one that has a vertical asymptote. And again, it's not always clear from the picture, so you need to know that if it's a natural logarithm or really any logarithm, this right side is going to continue traveling up, even though it looks like it's doing kind of a side curve thing. It does continue going up to infinity. So this is another positive infinity right end behavior. And the left-hand side doesn't exist. This function stops right here at 0 with that vertical asymptote, and so we've got another DNE for the natural logarithm function. And how about e to the x? Of course, this is the inverse function for the natural logarithm. It has a horizontal asymptote, and then it curves and continues to go up. The right end behavior is pretty clearly going to positive infinity. The left-hand behavior is pretty clearly a horizontal asymptote. So here we go. Now this last function that I'm going to give you is technically not a new function family, but I just want to make sure that you're paying attention. What do you think about e to the negative x? Cool, so there's a couple ways you could think about this. Some of you may remember the negative exponent turns this e into 1 over e to the x. In other words, it makes the base of your exponential function into a number that's smaller than 1, which means that this is exponential decay and the function's coming down. It has the same shape as exponential growth, but the asymptote's on the other side. The other way to remember this, if you don't like the negative exponent thing, is just remember that when you put a negative in where x is, for any function, the effect on the graph is to flip it over the y-axis. So we flipped this over that way and ended up with this shape right here. Regardless of how you remember it, you need to know what this looks like and what it means numerically. And when you look at the graph, you should be able to recognize that this one has a right end asymptote, and the left end is going to positive infinity. So this would be e to the x up here, sorry, negative x, and we would have our asymptote, e to the negative x here. Now, looking at our table, we're noticing that there's kind of a little bit of sparsity here. Give me another function that doesn't exist. Well, sine and cosine actually are going to belong in this category on both ends. And it's actually not that no functions go to the negative infinity on the right end. It's more likely that any of these functions multiplied by a negative number would end up down here in this category. So the normal parent functions usually go up on the right. We're just used to seeing that as the normal way to go. But obviously many functions do have right end behavior that goes to negative infinity. And you'll see that in the next couple examples. The first limit asks what happens to x plus e to the negative x as x approaches positive infinity. Well, if this were just x, we would know that x approaches infinity, as x approaches infinity, obviously. And e to the negative x, if you remember, that's the descending exponential decay function. Well, this one's going towards 0. So imagine adding really, really large numbers with numbers that are closer and closer to 0. It's pretty easy to guess that this limit is going to have positive infinity end behavior. But when we get to the second one, it's not quite that easy. X goes to negative infinity, but as x goes to negative infinity, e to the negative x goes to positive infinity. And so then you have this kind of contrast. You have smaller and smaller and smaller numbers being added to larger and larger and larger numbers. And we don't really have a good way of knowing how they balance each other out. We know they're acting in different directions, but this is one of those infinity minus infinity situations that we really can't evaluate. Similarly with these last two, we've got positive infinity being divided by positive infinity. It's really just not clear what's going to go on with that one. And we have positive infinity being multiplied times something that doesn't exist. Well, this one's actually easy because if you can't plug in negative numbers to the ln function, this function just doesn't exist on the negative side, and so the answer to the limit is dne. But the last one and the second one provide a mystery in some sense. And in order to evaluate these, we need to understand kind of a relationship between the different functions. Because we have lots of functions that go to positive infinity, we need to know which ones go to infinity kind of with the most strength. So grab your graphing calculator, and I'm going to ask you to graph all 6 of these functions in the same viewing window. I would recommend starting with this viewing window and then zooming out to this one and then to this one. And I'm going to have you answer some questions about what you see. Just a hint, you might want to use the trace button. If you use the trace button on your graphing calculator, it'll allow you to jump from function to function, and you can look in the top corner to see which function you're actually looking at to help distinguish between the different lines. So hopefully what you learned from this exercise is that the function that may seem to be the largest initially isn't always the largest in the end. Here are all of my functions, 6 of them. This is actually the ln function up here at the top, and we've got e to the x down here in blue. Watch what happens as I zoom out, and hopefully you already saw this. So the ln function, although it starts on top, actually kind of curves over to the side and ends up being one of the lower functions by the time we're at 15. Similarly, e to the x, which started out pretty small, is going up so dramatically that it eventually overtakes all of the other functions. And right here, where it finally overtakes the quartic, the e to the x function seems to be going most dramatically towards positive infinity. And now I'm really zoomed out, and I'm going to adjust my window because I really only care about the right side. And once you zoom out far enough, you can see that each of these functions is kind of irrevocably set in a hierarchy, where the natural logarithm is always going to be the lowest from here on out. The linear function's always in the middle. The exponential function's always going to be the highest as we get out to the right end. So this is actually not just a fluke, it's not just by chance with these functions. There is a hierarchy of right end behaviors. And this hierarchy is a rule that's going to allow you to evaluate combination problems. Exponential functions, as we go to positive infinity, are always going to go to infinity fastest. They're the most powerful ones. And really hold on to this visual. This blue function, after we got out of the mess near 0, shot straight up, faster than anything else. X to the a, and we're talking about where a is a positive number, this represents all of your polynomials, all of your linear functions. It actually also represents your square root function because a square root has a 1/2 power. Anything where you have x to a power is going to be somewhere in the middle. And obviously higher powers like quartics go up to infinity faster than medium powers like square or linear, or this green is the square root, which is a power of 1/2. And then finally, the weakest functions that go to infinity are logarithms. So what this means for our limits is that when we evaluate a limit, we were initially confused by the whole negative infinity plus infinity, but actually if this is the more powerful function, e to the x is higher on the hierarchy, we really only need to pay attention to this one, and this is actually an end behavior model, and so the end behavior follows the more powerful function. Similarly here, the more powerful function is the exponential on top, so we really only pay attention to that to determine the end behavior. Use this idea, looking for the more powerful function, and solve some on your own. And here are the answers as I've worked them out. In each case, I've circled the more powerful function, which then became an end behavior model. Notice that if you're going to negative infinity, e to the x is no longer the more powerful function because at negative infinity, e to the x goes to 0. The last one doesn't exist because of